sklearnmetricspairwisechi2kernel. Description: the chi-squared kernel is a popular choice in computer vision, particularly for image classification tasks. It measures the similarity between two histograms based on the chi-squared distance. Inputs: X, a 2D array of shape n samples. N features, representing the input data. Each row represents a sample, and each column represents a feature. Features are expected to be non-negative and represent histograms. Y, an optional 2D array of shape n samples to n features. If provided, it represents a second set of samples. If not provided, it defaults to X, meaning the similarity between samples within X will be computed. Outputs: kernel a 2D array of shape n samples. N samples 2 if Y is provided. Or n samples if Y is not provided. The values in this array represent the pairwise chi-squared kernel values between the samples in X and Y, or X itself if Y is not provided. Steps: calculate the sum of elements. Calculate the sum of all elements in each histogram. Compute the chi-squared distance for each pair of histograms. Calculate the chi-squared distance using the formula sumx y2xy, where x and y are the corresponding elements in the two histograms. Exponentiate the distance. Exponentiate the negative chi-squared distance by a given gamma value. Gamma 1 by default. This transformation ensures that similar histograms have higher kernel values closer to 1 and dissimilar histograms have lower kernel values closer to 0. Return the kernel matrix. Return the computed kernel matrix, where each entry represents the similarity between two histograms. Metrics: none. This kernel is designed for similarity computation, not directly for evaluation. Visualization plots. Heat map. A heat map can be used to visualize the kernel matrix, where each cell represents the similarity between two samples. Brighter colors indicate higher similarity. Fine-tune parameters. Gamma, a float value, default one that controls the exponential scaling of the chi-squared distance. Higher gamma values emphasize smaller distances, leading to a more sensitive kernel. Lower gamma values dampen the effect of distance, resulting in a less sensitive kernel. Uncertainty methods. None. This kernel is a deterministic method and does not inherently involve uncertainty. Challenges and fixes. Challenge 1: high dimensionality. If the input histograms have a very high number of bins, the chi-squared kernel can be computationally expensive to compute. Sample use case: image classification with very fine-grained color histograms. Fixes: feature selection. Reduce the number of features bins by applying feature selection techniques. This can significantly speed up the computation. Dimensionality reduction. Apply dimensionality reduction techniques such as PCA or tsna to the histograms before computing the kernel. Challenge 2: sparse histograms. If the histograms are sparse, i.e., contain many zero values, the chi-squared kernel can be unstable. Sample use case: text classification, where words are represented by their frequencies. Histograms in documents. Fixes: smoothing. Apply smoothing techniques to the histograms, such as adding a small constant value to all bins. This helps to prevent division by zero and makes the kernel more robust to sparse data. Alternative kernels. Consider using alternative kernels that are more robust to sparse data, such as the cosine kernel or the Jensen-Shannon divergence kernel. Challenge 3: unbalanced data. If the histograms are unbalanced, i.e., some bins have significantly more counts than others, the chi-squared kernel can be biased towards histograms with higher counts. Sample use case: image segmentation, where one class has significantly more pixels than others. Fixes: Normalization: normalize the histograms before computing the kernel. This ensures that all histograms have the same total count, reducing the bias towards histograms with higher counts. Weighted kernel: use a weighted version of the chi-squared kernel where each bin is weighted based on its relative frequency in the data. This can help to reduce the impact of unbalanced histograms.